So once you generated this alignment file, first you have to save this alignment file. Once you save this alignment file, okay, this file is in PIR format. Okay, we call this one as a PIR database format. So for this database format, we have to write a statement for every sequences. So if you're not able to write this statement here for each and every sequences, it's the program, the model may not able to recognize what exactly it is. Okay, so how the statement we have to write means, for example, for the target sequence, this is your target sequence. Okay, for target sequences we have to write start with the sequence colon. So name of the sequence, you can see here, but always you have to remember, you should not miss all these things. So greater than and capital P1 colon, and after that you have to write down the name. So you have to mention the same name here, target colon. So what is the first base, the number of the first base pair, sorry, number of the first amino acid, 1. Next colon should be chain. What is the chain of this one? As the structure is unknown, we don't know which chain there belongs to. Okay, and the end amino acids. So here, what is the end amino acid number is there. So you can check this one in a Word. So copy this one. So here I'm going to paste this one in a Word. So here let us check this one, how much the length is, 419 amino acid. Okay, so it is started from 1 to 419. So next column is, you can write the what is the organism name. So here you can mention what exactly the organism it is belongs to. For example, if you know that one, a human, you can just write the human. So next one is, you can write the protein name here in this column. For example, if I want to write the human, okay, you can write human here. If you want to write protein name, you can just mention here the protein name. So here, and you can write the source, what exactly the source of this protein, just mention that one. And in the last column you can mention the resolution factor. What is the resolution factors are there? You need to get this experimental structure for experimental structure, and the final one you can write down the R factor. So this resolution structure and R factor, you can get it from only crystal structures, experimental solid structure. If you are confused, you can exclude this information, but you have to mention all the columns perfectly. Okay, so all the columns perfectly. So here the human organism name, and here the enzyme, protein name, what is the source, and finally you will get the R factor, and last you have. So you have to observe 9 colons you need to have, 1 2 3 4 5 6 7 8 9. Even if you miss a single colon, you're not going to get the results accurately. So you're going to get an error. Okay, you have to remember this point. So now you have to write a statement for the structure. So here you have to start the statement with the structure, not with the sequence. So sequence only for the template, sequence only for the target. Structure statement should be only for the template, experimental solid template structure. And you have to mention which type of experimental has been done, whether it's X-ray or NMR. Okay, you can check directly from that PDB file 6WZQ. You can see here they use the X-ray diffraction to solve the structure of this protein. Okay, so here write down the statement as X. Okay, so I will remove this PDB chain, and here colon. Now we have to write down the PDB name 6W. So be on safe side, you better to copy this region exactly. See, even single letter, if you miss the single letter, it's going to show you error for you. So .pdb. So now we have to write what is the starting amino acids are there in this PDB structure. So there is a few options are there. You can directly check from the PDB format file. Okay, so open here PDB format file, check what is the first amino acid is there. So where exactly started? It is started from 251, but when you see the structure of the 6WZQ, when you see the sequence of this one, the first amino acid is a 309. okay, not the alanine. Okay, so it's threonine is not the alanine. Okay, so it means there is some amino acids are missing in the crystal structure. So don't worry about it, you will always find the missing residues in a crystal structure. Okay, so some amino acids are always you will find missing in a crystal structure. So we have to do manual curation, we have to manually remove the amino acids. Why the missing amino acids will found mean sometime if for example if the some of the regions in the protein structure is not very rigid in the crystal structure, the experiment may not be able to solve the structure of that particular region from the X-ray diffraction data. Therefore, in the PDB file you can find these regions reported as a missing residues. You have to type here, okay, Control F, type missing. Okay, so here I will go to up. So missing residues, you can see here there is a missing residues are there. So it has been started from somewhere around methionine, lysine, serine, histidine, something is missing. So you just need to type what exactly, where exactly the location, what is the amino acids which has been missed in this region. So by looking at this one, we can say that it has been started from threonine. So here, right down here, you can see here, I can see here this the threonine residue. It is 247. Okay, so here I'm going to minimize this region. So what is the region of missing here? Threonine. Okay, so after threonine you find lysine here, okay, and one more lysine is there, threonine 247, 248, 249, lysine, serine, S. So up to here threonine, lysine, serine, 247, 248, 249, 250. Okay, now we will check here where it is located in this sequence. You can see here this is the region where the missing residues are there. Remove this 4 residues manual. Okay, you can delete this 4 residues at a one spot. Okay, so here I'm deleted all the 4 residues, and you need to fill with the gaps 1, 2, 3, 4. Okay, even if you type a single letter extra, you are going to get an error. Okay, so now save this one. So now what is the starting amino acids are there? You can check here what is the starting amino acid. So it has been started from 251 amino acid, 251 amino acid. And what is the chain here? So you can see here what is the chain. It's a chain A. It's chain A. And what is the end amino acids are there? What is the end amino acid? What is the last amino acid or end amino acid? Okay, so it has to match with your sequence. Okay, so you can see here the proline, here also the proline is there. Before that one the phenylalanine is there, phenylalanine. Okay, you can cross check that one to be on safe side. So threonine, okay, you can see threonine is there. Okay, so it's fine. So the last amino acid is 364. 364. Okay, now as I told you, if you want you can represent the organism name or enzyme name, source, R factor. Okay, so R factor and resolution factor also you can mention. You can find here as a resolution of this protein, this crystal structure in the top column. See here the resolution value also is available here, and also the R value also you will find. You can see here the R value. You can mention these values here in these 2 columns, in this column and this column you can mention that one, but as I told you it's not necessary, they are optional. So now we finished this first template statement. Now we need to come to the second one. Okay, so we close this one. Okay, so here let us open this 6M. Okay, so here, alright, let's start a statement for this one. So remove this part. Now start to write structure, structure. So what is the structure it isn't solved? Let us check this one. It's also X-ray diffraction. So click on X So what is the name of this enzyme? What is the name of this template? 6m3m.pdb. okay, so now what is the first amino acid it has started? Okay, so you can see here, let us start this one, check this one. So it is started from aspergine. Okay, it is started from aspergine. Okay, so here it is aspergine min N. Okay, still I think there are also some missing residues are there. How we'll find the missing residues? Simple, missing, type this missing here. So you'll find the missing residues. Now you can see here missing residues are there. From here itself I can say it has been started from arginine. You just need to find the arginine here and start to continue to write down by looking at this region. So here arginine. Okay, so start here from arginine, search for arginine, proline. Okay, 42, 43, 44 is the glutamine, Q, glycine, leucine. Okay, sorry, glycine, leucine, proline, and again asparagine is there. Okay, so here 42, 43, 44, 46, 47, 48, this 48, these residues are missing. Let's search this one. You can see here we found this region. Okay, so here 1 2 3 4 1 2 3 4 5 6 7 amino acids are missing. So now delete this one. 1 2 3 4 5 6 7 residues. So here we deleted this one. Now it has been started from asparagine. You can see here still, you can see here some of the residues are still missing. I can see this chain A, glycine. Okay, let us find this glycine also here in the, whether it is there or not. Glycine. Okay, aspartic acid D, glycine K. Okay, so these 4 residues are missing. Let us find this one. You can see here the region is located here. If you want to cross check that one whether really they are missing or not, you just go to the PDB file here. For example, I'm going to go to this particular region where 97 number residues are, 96 residue. So here 96 residue. So you can see here clearly 96, it has been jumped to 102. It means 97, 98, 99, 100, 105 residues are missing here. Okay, you need to delete the 5. 1 2 3 4 5. Okay, let us see is there any other residues are missing. Still I think you can see here glutamic acid 175 is there, still it is missing. You can cross check that one in the end of this file. So we have only a sequence until alanine 174. So you can see here alanine. Before to this one alanine, we'll find the tyrosine. Okay, tyrosine is there. Okay, let's remove this part also. Okay, so now start write the statement. Okay, so what is the first amino acid? The end amino acid is 174. The first amino acid is 47, I think 49. Okay, chain A and 174 the end amino acids. Now write down 1 2 3 4 5. So now we created the PIR format file, PIR format alignment file. Okay, save this one, Control S or save. Okay, so once we have successfully installed the modeler, so now we need to get 2 very important files to perform the modeling step. Okay, so here how you need to go to the C drive. So go to the C drive here, click on the program files, click on Modeller 9.24. This is the advanced version I installed. Go to example, click on auto models. So here we need to have 2 files. One is loop file and model multiple file. So once you paste this model multiple PY file, Python script file and a loop file, so we have to edit these files. Okay, so these are the script files. So go to the model multiple file, open with Word. Okay, Notepad. So first thing, we have to change some of the parameters, file names we have to change. Okay, so here alignment file, what is the alignment file we have? So we name this one as a1. Okay, so now what are the known templates are there already available? One, it's there, you can see here 6M, 3M. So exactly you have to mention 3M. So next one is 6WZK. Okay, so what is the sequence name? You can check the sequence name in alignment file. So open the alignment file, you can see here what is the sequence name, target. Okay, so here the sequence name is target. Okay, so now we gave the input file names. Along with this one, we have to give the quality assessment. Once some homology modeling has been created, it has to check what is the quality of that particular protein model. So in Modeller, we have an option. Okay, there is a dope software is available where it will check the quality of the protein. So once a model has been created, we have to use separate command to check the quality of the protein. So I think we can add here itself. I just want to give a small trick for you. Okay, so here remove this bracket and put the comma here. Okay, so now go to the tutorial. So Modeller tutorial will find the internet, just type on Modeller tutorial. So at the fourth step you will find the dope command. Okay, so here up to here, from access to this region, copy this region. Okay, so here paste this region after this string. Okay, paste this region and this one. Okay, so after that, so how many models you want, how many confirmation you want? You want only one protein model or you want multiple confirmation? Always you need to select better to select a multiple confirmation. Why? Means we don't know in which confirmation you're going to get a highly good or well characterized homology model. So I'm going to generate up to 100 protein structures, so it's easy for me. So why? Means even you can generate 10,000 also. Here we have a dope score. Based on that we can assess which one is having a good quality. So here, so once I've done this one, save this file. Okay, so now let's run the command. Okay, go to Modeller. Mod 9.24. okay, and model multiple.py. You can see here in background there is so many scripts files are generating. Okay, so here there is D format files are there, and also it will generate the B format file, and also the volume format file, and also it will generate the B format file. There are 3 different configuration it will generate. So out of them, they will find in a description itself the PDB format file. You can see here the first model has been created. Like this, it will generate 100 models for you. Okay, so just it will take 5 minutes. Let us pause this video. Once it is done, we will continue. It is generated. As you can see here, it's completely 100 models has been generated. It just took me 10 to 15 minutes for me. Once it is done, it will show you a symbol like this. Okay, so what is come back to your main location. So it will generate a PDB file along with the supporting files also it will generate. Along with that one, you will find the log file, okay, in text format. So this is called as a log file. You can just click this log file. If you click the log file, at the end of this log file, you will find the dope score. So the dope score should be always in negatives. If you have a more negative value, it means the structure is highly accurate. So we need to find out of 100 structure which one is having a high number of high quality structure. Okay, copy this one. So open in Excel. So here paste this one. Okay, here to data, so text to column. First row is set first row. Click on filter. Okay, so here smallest to largest. Okay, so now you can see here this one, this structure 71 B99071 structure having a very high quality, so compared to others. So we are going to consider this 71 structure for further analysis. So here go to 71. So let us find where exactly it is there. So these are the supporting file. You will find a D and V. These are the supporting file. These are the not needed. These are not necessary for us. So we need to find the PDB file 71. So here we have the 71 PDB file. Now you can copy this one. Okay, this is a 71 file. Is the file we have. So you can open this one in a PyMol. Okay, just go to the PyMol. Any visualization example you can use. So PyMol, Chimera, you can use any easy one. Okay, so here drag down this one. So you can see here the structure is not looks so great. So why means this loop region, these are the chain region which is completely absent. Only this loop region you can find this, some of the helix regions are there. This region has been crystallized. Okay, or this region has been not they're not completely folded in the protein. You have to remember the protein structure need to fold properly to get the active form. Okay, so here in Modeller we have one more options are available. If you got the sequence like this, we can do it in two ways. If you perform the MD stimulation, if you use the GROMAX MD stimulation, we can fold the protein structure in proper way, or we can do the loop optimization in Modeller itself. Okay, I will show you that part also, how we can optimize the loop. But first we have to find out what is the location of this loop, which particular location you want to fold. For example, I want to fold this particular region. So just find out, click on the sequence. So here this region is located, I think at the end over here. Okay, so I want to from 300 and approximately from here 366 to I want to fold 419 region. Okay, so 366 to 419 region. So here go to COVID-19. So here you remember I pasted one more file for you called as a loop. Okay, open this loop, open with this. Okay, so here now we need to change some of the parameters. Okay, so here we are going to use the structure 71 PDB. Why? I mean, this is a protein structure, we got the highest values. So this is the PDB file. Always you have to select the PDB file. Okay, so here paste this PDB file. So what is the sequence name we gave? We gave the sequence name as a target. So now how many models you want? Now here also you can generate multiple models for the same sequence. Okay, so I want only one model. So now here there is option is available for you. If you want to fold the loop one or more loops, you have an option. Okay, for example, in if you want to fold three loops, fold three loops, you remove this one. Okay, so here remove this area and remove this slash. If you don't remove this slash, the program won't recognize that one. Okay, remove the slash and you can start to write one more string here, self residue underscore range. Okay, here you can mention the name the same as they mentioned in the above. Okay, so let us show you, show you example for you. Okay, so here in one region we are selected from 365 to the end amino acid 365 to 419. So I'm going to write 365 419. Okay, so here I close this bracket. So in the above, so I have to change a few more loops are there. You can see here some of the loops are not very odd to me, so especially this starting regions. Okay, so from loop label residue from first amino acid 2 until I can see here the loop has been bended until I can select 48. 1 to 48 I will select. It's here in the first one, 1 to 48. So even I can select the second loop also. There is, you can see here one more loop, it's not completely folded, this region. You can see this region also, it's not properly folded. Okay, I just need to look at that particular region. Oh yeah, here. Okay, so okay, so it's fine. So let us see what is the starting and what is the ending. So 175 is a starting and 244 is the ending. 175 is starting and 244 is ending. 244. Okay, I'm just creating one model. Okay, so if you want to create multiple models, for example, if you want to create 100 models also, you can generate it. Now let's run this one. Now you can see here it's going on, it's working. Now the loop has been created. Now you can see here the BL. So if you find this BL region, it means this is the loop region. Now you can see here clearly there is a slightly proper folding has been there, so compared to the previous model. So compared to previous models, you can clearly see there is, you just need to click align to molecule. Now you can see here there is alignment is there, and also you can find clearly the one fold. This is the improper fold. You can see here this is a proper folding is there compared to the previous model. Okay, so even if you increase the number of cycles, like if you increase to 1 to 100, maybe you have a chance to increase the folding of these particular side chains in proper way. Even you can rerun the loop optimization until you will see a clear, very highly accurate protein folding. So once you've done this one, next step is you can go for the validation by using the PROCHECK server is there. So I will show you what is a PROCHECK also. So here verify 3D, go to verify 3D. Okay, here in verify 3D, click on this PROCHECK. Here we are checking the stereochemical quality of the protein. Okay, so click on the only we're going to select this protein. Okay, so paste it here. So here file, go to desktop. Okay, so here loop region with optimized one. Okay, so once you done this one, it will show you various parameters, various files for you. Okay, so here out of them you can use anything. So I personally prefer to use a Ramachandran plot. Okay, you can see here the quality it will show you. Generally your protein quality should be more than 90%. So at least you need to maintain the good. If it is if your amino acid residues are in favored region, 90% of your amino acid should be in a favored region. So then only your structure is highly accurate. Still, I think your structure is good, 87%. Still, you can improve your structure by optimization, loop optimization, further folding also you can do it. Even if you want to perform the 2max also, that is the best option for us to do the proper folding further putting. Okay, so this is why it has happened, means here your identity is very less. So you can see we have cumulatively we have only 40 to 50% of identities. If for example if you think that and also remaining structure is completely unknown, things that if you have a completely 60 to 70% of the structure is available, then the homology modeling, it will be going to give a highly accurate results for you. Okay, so I hope you like this video. If you have any doubts, any clarification, you can send a message to me in a comment box. Okay, you can send an email also to me. Okay, thanks for watching. Please like, share and subscribe to more videos on this bioinformatics content. Thank you.